so whisper, I can understand what you're talking about, all right? Thanks for coming here, and I'm going to have a couple of pens here, and this pen will only given to those who are asking the question, okay? Now, before I'm giving the presentation here, I would like to know how many of you know what is the computational geomechanics? Any ideas about computational geomechanics? What do you think about this? What does it mean? What is computational geomechanics? We use the computer to calculate Earth. Good answer. Good try. What do you think?
In my opinion, there's a lot of categories about computer like machine learning, and we can analyze about the component of soils, like friction or even
Component of soils.
Yeah.
Okay, so talking about soils, analyzing soils.
Yeah, analyze.
What do you think? Sensing, analyzing soil. When you're talking about geomechanics, all about soils. The weather. Soil, weather, timings. Okay, that's interesting. What do you think? No? No idea? You can tell from his names, right? What do you think?
I think it's around simulation of the behavior of the body against promoting practice of the environment and the structure and mechanism.
Yeah, so structure interaction, simulation, the behavior of soil. That's a good answer. What do you think? Using machine learning. Yeah. Using machine learning to predict soil behavior. That would be the answer, right? Okay. Any other question here? No? Okay. All right. So that's interesting because many of our students actually understand geomechanics in a very different way. Especially in Vietnam, when we're talking about geomechanics, we're talking about soil. Geomechanics is not just about soil. It's very complicated sub-of the discipline. I'm going to show you what does it mean by this and what can you do in terms of computational geomechanics. And some of the work I'm presenting here is extensively conducted in my own research group at Monash. Okay. How many of you know Monash? Can you raise your hands? How many of you know Monash? None of you know Monash? Really? Really? What is the best university in Australia? When you're talking about Australia, what university are you normally referring to? What university do you know in Australia?
I think I know the first thing I think is Monash, and the second.
So you know Monash, you should raise your hands.
But in the other side, Melbourne.
Monash, Melbourne.
La Trobe.
Latrobe.
La Trobe.
What university do you know? You have no idea about university in Australia? Yeah? Okay. Melbourne. Why do you know Melbourne? Is it because of the name of the city? There. Okay. How about you? Melbourne. Is that the university that sponsor the Olympia, right? So how would advertising they be? Okay. All right, so I'm going to introduce you to a very brief about Monash University. Just giving you an idea of what is Monash, where is Monash, what is the size of Monash. I'm working at Monash for 10 years. I'm graduated from Ho Chi Minh University of Technology. I then went to Japan to get my master and then PhD degree. And then I worked in Japan for 5 years. And then I joined Monash in 2012. And then I've been there since then. And I'm very proud to be at Monash because of this. Okay? So what I'm going to do now is I'm going to quickly give you a brief introduction about Monash University. Why Monash? And some of you here is actually, most of you, or some of you, you're actually going to join a 2+2 program with whatever university. So I'm going to show you a little bit about this Monash-HCMUT 2+2 program. And then I'll focus more on this computational geometry. This is the section, the focus of my lecture today. But I'm going to present it in a very simple way, right? In a nutshell, so that you guys will understand what it means. There will be, how many of you know Newton's second law? Come on, raise your hand. Newton's second law. Newton's second law. Come on. Don't tell me you don't know that, huh? Alright, so at the level of Newton's second law, alright, if you all know about Newton's second law, you should be able to understand my lecture, alright? Okay. So we start with Monash University. What is the Monash? So if you're talking about Melbourne University is a very old university. But Monash is relatively young university. There are 60 years since it is still development. It was established in 1958, but now it is the largest university in Australia. And also, it is one of the top universities in Australia. Now, you know, if you're talking about Australia, you're talking about 8 top universities. You say group of 8. Glasgow, Swinburne are not in the group of 8. Okay? So group of 8 are including Monash, Melbourne, Sydney, Queensland, UNWS, Sydney, and then ANU, Australian National University. Okay, so those are top universities in Australia. And Monash is one of those. Okay? And think about a university that was established in 60 years. And they are one of the top universities. And look at their ranking later. Okay? So where are we? So we are, this is Australia, right here. And here, you see this corner here? This is the Melbourne. And then right here is Sydney, Adelaide, Perth. So Monash is located in Melbourne, but it's not in the CBD, not the center of business. It's around 50 kilometers from the CBD. And that location is pretty good because for international students like you blind, stay in CBD is very expensive. You stay a little bit away from CBD, and then you can focus on study. At the same time, you can travel to the city for coffee or whatever purposes, right? During the weekend. So that's normally I eat, right? We change the few minutes. Monash actually have the campus, the main campus in Australia, Clayton. In Australia, we have a couple of campuses. We also have the campus in Indonesia. We have campus in Malaysia, China, India, and even Italy. And we have 100 plus partners of university collaborating with all universities all around the world. And this is the reason why Monash is the largest university in Australia. And this is the size of the university, to give you an idea of how many students we have. This is some of the iconic buildings. Didn't allow me to talk. This is some iconic building you can see at Monash. So we have close to 90,000 students, very large size, right? And we have around 18,000 staff. Okay. Now, going to ranking, probably this is the most important you guys might looking at, because when you study overseas, you need to study at the prestigious university. The prestigious university are measured by the ranking of research and education. So when you study at the prestigious university, your degree will be evaluated. Right? If you graduate from larger university, for instance, their ranking are much lower than us, not even in the hundreds. Okay. So this is the ranking. So we have been consistently in the top 100 university, the best 100 university in all over the world. How many universities in all over the world? Thousands, can you imagine that? And this year, we are, for the first time, we are now in ranking in top 44. This is the highest ranking we achieved recently. 44 in the world, right? Top 50. Meaning that at Monash, we are highly invest to improve research and teaching. That's why our ranking are rising. And this ranking will be very good for your future, being good. Okay? And then what else? Okay, and then employment, right? This is the very sort of the positive feedback we receive from CEO of a lot of industry. When our graduates actually went out of industry, they did excellent work. And that actually improved our reputation. And CEO after a company, large company, they came back and said that if they have opportunity to hire the graduates, they will likely to hire the Monash graduate still. That's why they are ranked number 54. Okay. This is the degree. So at Monash, we offer the system at Monash University. At Monash, the Monash University is a little bit different compared to Ho Chi Minh University. So this Ho Chi Minh University is focusing on engineering technology, but Monash, we have the range all of the disciplines. We have the laws, we have medicine, we have science, engineering, education, business, all in one. That's why the size of the university is also very large. So think about Ho Chi Minh University, they are this size. They are actually engineering university. So we call the faculty of engineering, and the size of the faculty of engineering is equivalent to Ho Chi Minh University of Technology. Okay. This is something that you want to further looking at. Now, how many of you are in civil engineering? Is that all of you are in civil? So what year are you? You're in civil? No?
Civil engineering.
Civil engineering. How about you? How many of you are not in civil? Can you raise your hand? So what are you?
Food engineering.
Huh?
Food technology.
Food technology. Okay. How about you?
Computer science.
Computer science. And how about other students?
Mechatronics.
Mechatronics. Okay. So the different disciplines, right? So I don't know where you have here. So this is the civil. We are here. I'm from civil. So we are ranking number 27 in the world. Top 27, imagine that. And then mechatronics, I don't know mechatronics, but I'm definitely in top hundreds. Okay? So definitely there. And some other food engineering probably belong to the chemistry or this chemical engineering. Okay. And one of the most important is in terms of engineering. Whatever discipline you are belonging to, engineering we are number one. This is the most important. Melbourne University, they are big name because the university are actually linked to the name of the city.
Yeah.
So people know about Melbourne City. So when talking about Melbourne University, they know, okay, Melbourne University. But who is the best? Monash. Okay. I'm proud. I'm very proud. Because wherever I go, I'm proud of Monash University. Okay. And this is the thing, when you're working in a number one university, you are always proud and people will know you. Okay, so this is the good thing. I didn't have the opportunity to study in this top university. I graduated from Ho Chi Minh University, but then I went to Japan. Japan didn't care about the ranking system. Okay, but then I ended up at Monash. Okay, I have done different things. This is an undergraduate program to give you an idea. We have a chemistry. Each of these is corresponding to the bachelor of certain given discipline. For example, we have a Bachelor of Chemical Engineering, Bachelor of Civil Engineering, Bachelor of Aerospace Engineering. So all of these are single degree. But on top of that, at Monash, we also have the double degree. That means you study extra 1 or 2 years, you get 2 degrees. You can have the Bachelor of Civil and Bachelor of Commerce. We mentioned that Bachelor of Civil and Bachelor of Law. So you have both degrees. This is a very good thing because after you graduate, you can work either as a civil engineer or as a lawyer. Okay? So that is the thing we're giving students a lot of flexibility to enhance their career. Okay? This is something we really focus on. And then in terms of the graduate program, so we're having different coursework program. We're having the accelerated master program, which is 5 years, meaning that you study 4-year bachelor degree plus 1 year, then you get a master degree. Or you have bachelor degree, you can enroll to the program to study 1 year for master bachelor, okay? Or you can actually enroll to this what we call Master of Professional Engineering. This is the program designed for post-engineering degree or non-engineering degree. So even you are actually having a degree in mathematics, physics, chemistry, whatever, not engineering, you can still do the Master of Professional Engineering, but it takes 3 years. Okay. So this is something we offer at Monash. And this is the research program. Now I actually take a lot of students from Ho Chi Minh University of Technology, and all of my students are gold or silver medal. Imagine that they study at Ho Chi Minh, this Department of Civil Engineering. When they graduate, they are number 1, and they come to my lab. So I have around 20 students so far. They all gold or silver medal, and after they graduate, unfortunately they don't come back. They all stay in Australia for some reason. Alright, so this is the thing about the research. As a bachelor student, you can have opportunity to do research. Research program is 2 years, okay? And with the PhD program, 3 to 4 years. So if you are the bachelor graduate and your accumulated GPA is above 80%, you can enroll directly into the program. You don't need to study master. Okay? So those students who actually come into my lab, who got the gold medal, and then they study Doctor of Philosophy directly. After 3 years, they got the PhD degree. Okay? There's also the industry diploma program, where you study the PhD degree, at the same time you receive the payment from industry. So you work with the industry, you collaborate with them to solve their problem, and then you enroll to Monash, right? You study at Monash, at the same time you get the payment. See, think about that, right? And the salary is very high, 100,000 per year, salary. And after 3 to 4 years, you get the degree or the doctor PhD at Monash. And this is something quite important. Now, to some of you it may not be important, but to us it's important because it shows us how much money we invest to research, how much money we invest to teaching. This is very important because the university with less money or fund invested to research will not be able to show their strength. So this is the total income we taken from university students, right? Both local and international students. But this is the income we spend. So where's the rest of money come from? This is income from teaching. This is income from research. What do you think about the rest? Otherwise, we're going to bankrupt very soon, right? So we spend almost double amount we receive. This is the research fund. We, as a researcher, as a professor, who actually secure from government, from industry. Right? So for example, I have a project of multi-millions of dollars, and that project helped me to run my research. That project helped me to buy equipment to do research. Okay? So this is the huge amount, and this is the largest spend across university in Australia. Okay? And this is the facility to give you an idea of some interesting facility at Monash. Well, if you come to Monash later on, you can see. But some of the facility here, synchrotron. You know synchrotron? So we have synchrotron center located at Monash for us to do research. We have a range of industry partners. They actually place their lab or their sort of the research group at Monash to do the collaboration, right? And this is the new proposed sort of the railway. So in the next few years, there will be a train station directly connect to Monash. Right, I mean, you can easily hang out.
Yeah.
Right? If you have a girlfriend, boyfriend in the CBD, you can take the train and go there after the class, right? Easy. All right, now back to the civil. So this is, because I'm from civil, so I just show a little bit on civil. This is my department. So in my department, we have 48 academic staff, including 3 Australian research cultural, or we call the future fellows, and I'm one of them. So we have across civil engineering, we have only 3. Okay, I'm one of them. And this one is a very prestigious title given by Australian government to outstanding researcher to conduct intensive research in 5 years, within 5 years. Within that 5 years, I don't need to do any teaching. I only do research. See how good I'm a professor who doesn't need to do teaching, just doing research. Right? So normally in Australia or any other developed country, professor, they have 40% of teaching, 40% of research, and 20% of services. All right? This type will give me 100% of time doing research. So that's a really good thing. And this is the discipline civil. To give you a quick video to show some of what is civil doing.
Civil engineering impacts just about everything in our world. It focuses on the design, construction and maintenance of the physical and naturally built environment. From our waterways, our structural designs, transport network, geotechnical industries. As a civil engineer, you could specialise in structural engineering. Be involved in the design, construction, maintenance of buildings, bridges, tunnels, pipelines and all sorts of industrial structures. Thanks to civil engineers, we have fresh water running from our taps. Our dams and reservoirs integral to our water supply system, designed and constructed by civil engineers. In fact, civil engineers are often working on the heart of the city, planning, designing, and ensuring our roadways, busways, railways, roadways, and other transport infrastructure all run smoothly. They'll find innovative ways to manage traffic operation. Now, civil engineers even work under the earth. Geotechnical engineers work in the mining and petroleum industries, specialising in looking at earth materials to design tunnels, foundations, even landform contamination solutions. Established in 1961, Department of Civil Engineering at Monash-HCMUT has a solid reputation of teaching and leading research in civil engineering. Our civil engineering students have access to a vast range of specialised equipment and facilities, including the Near Horizons building. The options for civil engineering projects ensure endless growth with new trends towards building smart cities and improvements to infrastructure and transport. Civil engineers develop the future of our day-to-day lives. Civil engineering. Be a part of building a better future.
So that's civil. So we have 6 different disciplines within civil. So meaning that after you get the degree in civil engineering, you can working in a geotechnical firm, you can working in the water engineering firm, or you can working in structural engineering companies or whatever. Okay, that's a good thing of civil engineering degree. So you're not tied to a single discipline. So that's the advantage of civil engineering program. Now, go to that 2+2 program that some of you here are enrolling. It's quite a new program, and I'm was one of the people who established this program, so I have to mark the program to make sure that the background I'm mapping with a Monash degree. Okay? So you study 2 years with the University of Technology, and then now 2 years at Monash University. And this is 2 of the most important things that you need to consider when you study abroad. If you work in Australia, the degree needs to be accredited by Engineering Australia. If the degree is not accredited or not recognized by Engineering Australia, you're not able to work in Australia. So That's the very important thing. The second thing is the Washington Accord. It's very important recognition because graduate from Monash University, you can bring your degree to many different countries where they recognize your degree, right? Ho Chi Minh University of Science and Technology, I don't know how many countries they recognize. How many countries recognize in all the world? This one is Monash. We have about 30 plus. I think that's the university recognized. Now, entry requirement. This is the index that probably some of you know. We are the top university, so we only keep the top students. So you need to actually achieve at least 70% of students. Okay, at Monash. So we recruit the top students. Even in Australia, when we recruit the student, we have a very high entry requirement. Okay, so all the students actually enrolled at Monash are very outstanding. Okay. Some of the information you may want to know: living expense, tuition fees, living expense, and scholarship. From my understanding, that Monash will provide 10,000 each year to those who enroll to this program. It is a good amount. The living cost is around 22,000 per year. Tuition fees is that much. It's quite expensive, right? Compared to other university, Latrobe is much lower. Swinburne is much lower. There's reason for that. You don't pay for nothing. Okay, so there won't be reason for it to provide higher. Okay. All right. So finally, this slide about application process. If you need any information, feel free to contact Ms. Jensen, who can provide you all the information. All right. So that's all about my introduction to Monash University and program. We are part of my talk. Any questions? Anything that you want me to? Any question about it? Yeah? Feel free.
I have a question about your opportunity at job and work.
That's a question.
First, I want to ask you about the opportunity of jobs and work in Australia or another international company that work with Monash. If I have a student at Monash and after I graduate and I want to, instead of keep studying, I want to work for about 2 or 3 years and then I come back to study and I be approved.
Okay, that's a good question. So the question that's a good question. What is the job opportunity after your graduation? Okay. So this is a good thing, very good question, and I forgot to explain. So at Monash, we have what we call the co-operation. We call co-cooperation. So we collaborate with industry. In the last 2 years of their degree, collaborate with industry. We let students to work in an industry 3 months, 6 months, or even 1 year, paid by industry. Why enroll at Monash? Right? And then after that, you come back to Monash, and then you complete the degree. So during this course study, you work in industry, you build a collaboration connection with industry. That will give you a very good chance of getting the job after the completion of your degree. And this program has been extensively enrolled by many of our students because they want to secure the jobs after their completion. Okay, so that's why they enroll to this program. Now, definitely, after you complete your degree, you will be able to work in Australia because the degree at Monash is recognized by Engineering Australia. And if you want to find a job, you need to either enroll into that cooperation program, or you can actually doing some sort of the internship at industry in order to create a connection. You are free to work forever, or you are free to come back to do the PhD. With the with the bachelor degree and accumulated GPA of above 80, you can go straight to the PhD degree. Otherwise, you can come back and you study master degree and then study PhD degree. Okay? So that's why I said, unfortunately, all of my students, they don't come back. Because after the completion, they got on the job, either in the university or in the industry. Okay, and I understand it because research in Vietnam may be difficult, right? Because we don't, like us, when we receive the salary, we don't have to do anything. Because our salary is enough for raising the entire family. Right? So we don't have to worry about earning money for our living. Right? So, but in Vietnam, it's difficult. It's not that easy. So you have to take care of the family. You don't have time to invest in your research. Alright? So that's understandable if they don't want to come back. Alright, very good question. What else? Any other question you want to ask me? Yeah? Come here. Okay.
Teacher, I have a question for you. What do you think about when currently we are student at the University of Civil Engineering, when we apply for the exchange student 2 year, and after that we graduate in the bachelor degree, and you taught me about the scholarship, and we can pass the test to study doctor degrees. What do you think when our need the quality to learn about PhD degrees because master degree, and when we pass out the test, what do you need the qualities the student need to PhD degree? Because I think when you must have the test master, it's difficult to me to research in the PhD degree.
Without master?
Yeah.
Without master, okay. So, yeah, so we have two systems. Students complete their bachelor degree with a GPA above 80%. They can be drawn directly into the PhD program. So, with a GPA above 80%, those students are outstanding. So, if they are outstanding, they can follow with the program. So normally, with all students with a bachelor degree of above 80, when it comes to my lab, I need to spend 1 year to train them. Right? 1 year to training background knowledge, whatever knowledge, computational knowledge, and so on. And after that, they do research. With students who have the master degree, they're already ready to do research. Then they can go straight away. Okay? So normally, depending on student, but with 80% of the GPA, they are qualified enough to study PhD. And you need to also, if you really want to study PhD at Monash, then you need at least GPA of above 80% in order to get a scholarship. And there's a very good chance of getting the full scholarship from Monash if you graduate from Monash with a GPA above 80%. Good chance, very high chance. So we have every year, we have about 50 to 70 scholarships. Think about that amount. Every year I got 2 students got a full scholarship from Monash joining my lab. Okay.
What do you think about the Monash? Really the best good choice for the researchers after I graduate a PhD degree?
After you graduate PhD degree, if you want to get to Monash, you need to develop the track record. So everyone who wants to follow the pathway like me to become professor, you need a PhD degree, 3 to 4 years, and then after that you need probably 3 to 4 year intensive research at a postdoc, research assistant. So during that time, you need to develop the track records. Track records here mean publication, how many papers you publish, okay? And then after that, you need to apply to the university where you compete with so many people from different places. And of course, at Monash it's difficult because it's very ranking very high. The higher university ranking, the more difficult you can get a job there. But that means you need to have more motivation to develop a stronger research track record where you can compete with other people. Okay? some of my students, they got a job somewhere, not Monash. My PhD student, they got a job at some other university larger. They become a lecturer larger and Deakin University, Swinburne University, but they not yet to come back to Monash because they need time, okay? Right?
Thank you so much.
Yeah. All good? Yeah. Question?
Yes. I do have a question because right now in the fourth year, clearly I am not retired of the 2+2 program.
Yeah. That's all right. That's all
So
right.
if I still want to have a chance of studying most can you give me any suggestion? Should I just do it again and spend 4 years or further?
What is your GPA at the moment? Accumulated GPA? 70%. How many years left do you have? 1 year left. Then you probably get to the GPA of 75 maximum, isn't it? So that's the thing. If you're already in the third or 4 years, and your GPA is not above 80%, then there's still a pathway to study at Monash. You complete your, I wouldn't recommend you to go back, right, to study again. It's wasting time, wasting money, no point. You can study, complete your degree, and then enroll to some master program. During that 2 year of master program, you need to do very well. You need to make sure you get a high GPA, and you gotta make sure you get some publication. You know publication? What does it mean by publication? Anyone of you know what does it mean by publication? I mean, you're writing a scientific paper. You are doing research, you're finding something new, and you publish a paper. Right? So you need to write this. With a master degree, your supervisor should be able to help you with that. You need to do a very good master degree, love your publication, one, then you can consider applying to Monash. What is your discipline? What is your major? Mechanics, mechanical, or mechatronic? Mechatronics. Okay. Approach me later after you graduate, and I can give you some suggestions. Okay. If you want to study at obviously, if you want to get to Monash, you need to really. We only take our studies, right? But we also take the student because I understand that some students when they're doing the bachelor degree, they may lose focus. They're not getting very high GPA, but they are actually really good. I have a student who actually get quite a low mark in the undergraduate study, bachelor, but turned out doing exceptionally well because he was lazy or he was less focused with his bachelor degree. But he is very smart. So you can have a way to find out. Okay. All right. Anything else? All good? All right, I'll go into the main part. So it's a lot of time. How much time do we have? So I'm going to go through this computational geomechanics. Now this talk just really gives you the main purpose of this talk is to give you an idea of a correct understanding of what does it mean by computational geomechanics. Okay? So start here. So I have already asked some of you about what is the computational geomechanics. And some of you say about soil, about weather, about AI study, and so on. Okay, so this is my definition of computational geomechanics. Can you understand that? So we have computation, we have geomechanics. So computational geomechanics is actually the multidisciplinary research that require the mechanics of material, mechanics theory to study the behavior of geomaterial. That require the computational knowledge to solve the problem. Computation, you need to using some sort of advanced computational knowledge to solve the problem. Some of you can answer my question, simulation of soil behavior. That's right. If you want to simulate soil behavior, you need the computational values. But then, at the same time, you need to describe how the soil behaves. For example, you have a box of salts, or from any material. You compressing them, how they will behave. Wet soil, dry soil, they behave differently. Okay? So it's very complicated. So that's why the reason we're talking about multidiscipline is because we need the solid mechanics, with fluid mechanics, and we need aerodynamics. Right? By the way, do you know what is my bachelor degree? What do you think? You might think, what do you think about my bachelor degree? You might think my bachelor degree is civil engineering, right? At the moment, I'm working at a civil engineering, right? But my bachelor degree in aerospace engineering. Aerospace. See that? So I'm doing aerospace. I'm very good at the computational solid mechanics, computational fluid mechanics, computational aerodynamics. That when I'm moving on to computational geomechanics, I'll do so well. Okay, so this is the knowledge, background knowledge that I give them. So when I'm talking about the geomaterial, we start about the geomaterial. What is geomaterial? It's not just about soil. Right? Geomaterial is a very complex material. It's about soil. It's about cemented material. Concrete. Concrete is also geomaterial. Because when you mix in the concrete, you mix with cement, aggregates, you mix together. So geomaterial is any form that's related to granular material. So that's granular material. You have a sandy soil, sand, you have a porous system, you have a rock, you have concrete. All of these are classified as geomaterial. Okay? So don't just think about geomaterial as a soil. So I'm working with people in the structural engineering. I'm predicting the behavior of concrete. I'm simulating or predicting the failure behavior of concrete. Still, I also do that as well. So long as I have mechanics, I understand the mechanics, I can do everything. So those who have background in computational geomechanics can pretty much work in almost discipline. I'm talking about engineering. Okay? And then mechanics. Why do we need this mechanics? You can see that when you're looking at the geomaterial, it's actually a truly multi-phase. Multi-phase here because you have to looking at the solid. Solid is what? This aggregate here. It's a particle, right? Aggregate. And you need to looking at the fluid. When you're looking at the sandy material, wet sandy material, you have in the sand particle. And within the sand particle, you have this of the what we call lipid bridge. Okay, they connect sand particles together. Within the sand particle, you can have the air. You can see the interaction between solid, fluid, and air. It's very complicated. Think about steel, you only have one material, right? Think about fluid mechanics, only one material, water, right? Aerodynamics is on air, only one material. But here you have three materials, very complicated. How you describe the interaction with each other? So that's why we really need the multidisciplinary research to looking at how the solid, air, fluid interact with each other. Because if you want to, for example, if you want to have this system and you compress the system, when you apply the load to the system, soil particle or the granular particle here will carry the load. Water also carry load. Air also carry load. How you distribute them? Very difficult. So that's why you need all of the knowledge to looking at this sort of behavior. And then you need to look finally, you need to looking at you require the computation. What is the computation? So in a nutshell, computation is basically mathematical tools. You all learn mathematics, right? So computation is basically mathematical tools that are used to approximate this one. What is it? This is the first primitive, the second primitive. You need a mathematical tool to approximate this one, right? This is the computation in a nutshell, all right? So this is my definition of computational geomechanics. It's totally different from, to my understanding, our student here. When they're looking at the computational geomechanics, they're only looking at soil, which is incorrect. Right? It's a very complicated material, and this is the most difficult research area compared to any other discipline because of the multi-phase nature. Okay? So when you understand the concept, the next step will be how do I establish a computational framework How do I adapt this? Alright, so this is the procedure. If you want to model, you want to simulate a given problem, landslide or bearing capacity or design, structure or any system, you need to go through this process. You have to start from physical system. I mean, you need to looking at the problem from the real world, understand the problem, and then you need to make the simplification because you cannot consider everything in the world. So much detail, impossible to consider everything. You need to simplify it. You need to develop a mathematical model, and then numerical solution. This is an example of give you an example. We start with the physical system. So this is an example of what I did extensively in our research group. This is the landslide problem. It's one of the major disasters in Japan, even in Vietnam, Southeast country, and many other countries. This landslide is destructive because they can kill a lot of people. They can destroy the entire village. See? So this is an example of a landslide on the left-hand side. Is an example of landslide in the US, which almost destroyed the entire village. The question here is, how do we mitigate this problem? So if you want to mitigate this problem, you want to reduce the damage, you need to develop a foundational model and predict failure. So we start from here. We start from physical system. And this is an example of how this sort of thing can happen. This is an example of the very large scale equipment we conducted. Think about this one is 10 meter high. So we built this equipment and then we contract the slope and then we apply the artificial rainfalls and then we install the device in the system and then we measure the information inside the body of the slope. And then we try to understand the problem, what's going on. So that is the physical system. So when you're looking at the physical system here and you're treating a small sort of the element, you zoom in, you see this is the system you're looking at. You're starting from the system with a little water here, air. This system is the most stable system because the difference between poor air and poor water pressure here produce a very strong sort of a connection force. Okay? And then what happens is, when the rainfalls, rainwater, they diffuse to the soil body, these pores gradually fill with water. Eventually they become fully saturated and the soil loses their strength and eventually it's collapsed. This is a process, a physical process. By looking at the system, I understand the process. Now the next question would be, how do I model this problem? Right, so the next step is I need to go to some sort of the idealization. This is the system I understand from the test. And then I'm moving on the idealization here. You can see this system that for this system I have three phases. I have the air phases, I have water phase, and I have solid phase. They distribute randomly in this volume, right? This is a volume, let's say V. So idealization means I separated them. I take a solid volume, I take the air volume, I take the water volume, I separated them. And now it becomes one material. One material, one material. And now I develop the model for each of these phases. Because when it becomes one material, homogeneous, I can easily remove it. So I develop a mathematical model for one material, for water, for solid, for air, but then I lost the interaction. So I need to find a way to interact, describe interaction between them. How the water interacts with the air, how the air interacts with the soil. That is the physical law I'm going to impose. Okay? So but the good thing is, after I separated this, I can actually develop the mathematical model. Now I know all about the Golden equation because it will be complicated for the beginner. But do you know what the mass conservation equation? Mass conservation, that means the mass is unchanged, right? Momentum conservation equation, this is the Newton's second law. This momentum conservation equation describes how this element moves, okay? And then energy conservation equation, that's the energy are unchanged. We don't worry too much about this, we don't consider heat, okay? And interaction, I have the equation in place, but then I get interaction among all of this, okay? And then after, assuming I have Golden equation, then the next step will be, all right, now I have the model, I can solve it. I have the governing equation, I can solve the problem. This is the experiment we conducted. And this is the image of 3D scanning. Right? Scanner. We're using the 3D scanning to scan all of the failure morphology. And this is the simulation result that we predicted. This is the rainfall we apply on the surface. This is the initial slope, just like that. And the water coming in, I'm going to show this one later on. And at some point, it suddenly collapses. You see, it suddenly collapses like that. And this is the experiment of the measurement. So this is the process. You can see start from physical system, idealization, mathematical model, and numerical simulation. This is the ultimate aim that we want to achieve. Okay? I'm going to show you some of the examples later on. Okay? So when we're talking about this governing equation here, what does that mean by this? So I'm going to explore a little bit here so that you can understand a bit about this. Because just talking about mass conservation, momentum conservation, energy conservation probably have no meaning, right? But what does it mean by that? I'm going to give you a little bit on this. So if you want to looking at gas, so our governing equation, you might ask, okay, what theory do I need to study? Okay, what theory? So you can see that when you're working in the computational geometry area, pretty much this is the theory that you are required. You require continuum theory. Have you studied fluid mechanics? You guys study fluid mechanics, right? Fluid mechanics is continuum theory. You describe the fluid behavior, right? Solid mechanics, you study about solid mechanics. Hook law. Anyone know hook law? No? Spring hook law? Alright, let's see, okay? So this is the continuum theory. Think about fluid mechanics. The continuum theory is the theory that can be used to describe a continuum material. The constant theory is the theory that used to describe how the material will form under the high load. Okay? And finally, you have numerical methods. It's basically the mathematical tools. So I'm going to quickly explain some of this. I'm running out of time. I'll probably spend another 10 minutes, okay? And I'll quickly show you the result. So start from the continuum theory in a nutshell. It's all about continuum theory. Can you understand the continuum theory? I'll start from the left-hand side. I'm consider a car actually placed on the horizontal surface. And this car is connected to a spring. And it's pulling by a force F. Okay? Think about the motion of this one. If I want to describe the motion of this car, I have to use the Newton's second law. All of you know this, right? Definitely. The Newton's second law tells you what? I know the mass. This is what? Acceleration. That's correct. This is the force, applied force. This is the body force, mass, body force. This equation you understand, right? Unfortunately, this problem is only 1D. 1D problem because you only have one force component, right? Now, think about this one. Think about this guy. This is the, let's say you have the cubic element of solid, and you apply the force, you apply the load on this element. You cannot use that force because I can apply here, I can apply here, I can apply here, I can apply there, or even I can apply in this direction. So in total, I can have 9 different forces applied to this guy. So that force here is scalar in one direction, but this one has 9 components, so I have to use something else. So that's what I call stress tensor. This stress tensor represents the all of the force acting on this guy. Does that make sense? Okay? And the rest will be the same. Looking at this guy, looking at this equation, looking at that equation, I show you how the continuum theory is developed. On the left hand side, the mass, I'm going to consider a unit volume. So that mass equivalent to the density. So this is mass, basically, for one unit volume. Mass times with acceleration. I still have acceleration, right? This is the force. That force. And because at one time, this guy is actually carrying so many force. And I need to using this one to describe force. The rate of change of the stress with the space. And that one is the same. You see the similar thing. This is the one you see very frequently in continuous mechanics. You see it, or even in fluid mechanics, you see this. In fluid mechanics, this one is composed or consists of pressure and the shear stress. That is the equation. We call this the momentum conservation equation. And you can see the momentum conservation equation and the Newton's law, they are the same. Does that make sense? You understand here? You see the two equations exactly the same. But what the problem here? If you look at the equation, what is the problem? Can you solve the equation? Can you solve that equation? Yes? Can you solve the equation? Why? Why can't you solve the equation? Say it, come on. Why? It's okay to be wrong. Why? Why can't you solve the equation? Can you solve the equation analytically? That is the correct answer. Correct. Why?
Too many interactions and
Assume I know a direction. If you look at the equation, why can't you solve it analytically? Because you have this guy. This is the spatial derivative. You don't have analytical solution for it. Spatial derivative, right? You have to use the numerical method to approximate it, okay? So this is the idea, all right? And then, okay, I think I'm running out of time. All right, and then now you need the continuum theory. So this is the first one you need. So now assuming that I have it here, but the question will be, how do I calculate this? If I want to solve the equation, I need this guy. Right? I need the force. Then I need to calculate the force, right? So if I want to calculate the force, I need what is called the second component, I call constitutive theory. The constitutive theory, I have the governing equation, and the constitutive theory here tell me how I calculate the force. Think about a spring. If you have spring, this is the force. Force equal to K times X. This is the Hooke's law. And you all know about this, right? This F equal to Kx is actually the second component that I call the constitutive theory. And similarly, here I also have Hooke's law for the stress tensor. F equal to Kx. So this is the second component I need. Okay? And then finally I have the third component. So this is the numerical methods that I require. Sorry, John, I'm not running out of time. Probably 10 more minutes.
Yeah, we're going to ask some questions.
All right. Now we have a governing equation established, continuum theory. We have a constitutive model established. Now we need to solve the equation, right? How do we solve the equation? That's why we need a numerical methods. Okay? So you look at the equation. If you want to solve the equation, you need to find a way to approximate this spatial derivative. And that's where we need a numerical methods. And the key idea of numerical methods are basically convert this equation we call is the partial differential equation to the ordinary differential equation. For example, like the spatial derivative of stress can be approximated by the equation. This is a finite different method. Have you learned this one in your course? You have learned that, right? That's good. Okay. So this is the simplest way to do. And you see what does it mean by numerical methods? Okay, so I have three components, right? I have a continuum theory, I have a constant modeling theory, and I have numerical methods that require to form the basic concept of computational geomechanics. So when you're talking about numerical method here, I'm taking this example for the finite different methods. But in reality, we have many different numerical methods. Okay, for example, these are several examples that you can see. When you're talking about numerical methods, you can actually classify them into continuum or discontinuum. The continuum means you assume the objects as a homogeneous material. With discontinuum, you actually assume the object actually consists of an individual sum of the aggregate component. Okay? So when you looking at, I'm going to quickly go through. When you're looking at a continuum numerical method, you can have mass-based. Any of you know finite element methods? This is what we call mass. You see the mass, the grid. Okay, this is the mass-based methods. And this is mass-free. We don't have the mass. This is mass-free methods. And finally, we have this is another discrete numerical method. This is some of the numerical methods we extensively use in computational geomechanics. So So this is all of the basic concept of computational geomechanics. We have continuum theory, Gantt model, and we have a numerical methods. Okay? So then why do we need to use it? I'll quickly show you a couple of examples of why do we need to use computational geomechanics. So the first starting point of using the computational geomechanics is to the design. Think about this building. This is a very, this is the tallest building in Europe until 1997. And you want to design this building apart from the structural components. All right? You need to also looking at the foundation component right here. This is the foundation. How you actually design the foundation to make sure they can carry the superstructural load. And this is where the computational geomechanics plays a very important role. So we can use the theory I just explained to design, for example, this is an example of how we design this sort of the foundation system to carry the load. We can predict how much the soil deformed under the mega load, right? And also the surrounding soil is an example. Okay, so this is an example of what we can do. Or this is another example with the development of the urbanization. You can see that in many cases you have to excavate the soil, right? Especially when you excavate the soil or tunneling in a city. In many cases you have to do this sort of construction activity near the high-rise building. And it could actually affecting existing building. So we need to using this sort of numerical methods to predict, is it safe to do this sort of construction activity? This is another application. Okay? The other application is quite interesting is an example of design the mechanical structure. This is a project I did when back to the time when I was in Japan. If you look around, you can see it's an example of the structure, the mechanical work. This is the soil. This is also the mechanical structure. This is the soil. When you cut the slope, right, you need to have something to reinforce the slope to keep it stable. And we use this sort of the mechanical work to support the slope. Now, depending on the size of the slope, for this case, for example, the total height here will be up to 20 meters. And this block is actually around 1.5 to even meter block, very large block size. So, if you want to design this, you probably have to do some experiments and tests to optimize the shape. And it's very expensive to do this sort of thing in the field. So we can develop something using computational geomechanics. We can develop something like what I have here. This is an example of computational model we developed. We're having different scenarios. We're having, this is the soil, this is the block, and with different slope angle, right? And then we can test it on a computer. An example of if you actually load up to that level with a 40 degree, it can have some certain information, so it's not safe, right? So we can tell from the computer. And then here's another example. But if you actually reduce the number of blocks or reduce the height of the slope, it will stay stable. Okay? Or if you reduce the height of the slope but you increase the slope, it might actually become unstable again. So this thing we can tell. Okay? It's from the model. We can also design different shape, right? We can using the computational model to look at different shape because you want to optimize the material, right? And you also at the same time you want to reduce the weight of the retaining wall on the soil. And you can change the shape. So this is an example without this sort of the retaining walls collapse. And then when you design with 45 degrees, it's collapsed, right? But then if you actually reduce to 40 degrees, it's stable. So this is something we can play with. One, you have a conditional model developed. Or you can even look at this of the mechanical system here. As you can see, this is the cut excavation process. It's soil, you excavate the soil here, and you're having quite heavy, you don't actually have appropriate designs. Heavy mechanical, lighter one, or maybe appropriate one. And see what happens. It's quite interesting. Looking at heavy one. When you have, this is the without any support, this is a heavy one. Right? You actually have what you call here is a bearing failure. And then you have another one here, it's a lighter one, then you have what you call overturning failure. Right? This thing you can describe. But then if you design properly, like this, then it will save. Yeah. So that one is quite stable with the proper design. We can play with this. We can do using the conditional model to develop all of this. Or we can go further some sort of design. This is a very complicated problem. Looking at last line in which flow, this is one of the most destructive hazard. Right? We need to mitigate. So in the design practice, we normally use this sort of thing we call check down. So this is the debris flows. You can build the check down along the way to reduce the speed. You can use either check down or with the buffer system. You can have that sort of the column of concrete installed down the track. This is an example of the systems they installed in Hong Kong by working with them. So we can develop a computational model again to test and then to optimize the system. Is here an example of how the computational model can predict the flow through the buffer system. You can see that. Or you can even looking at this one. If you're looking at, right, if I don't want to use the buffer system, I can use the check down system. The check down, buffer, tone, short, buffer. I can use the computational model to predict what is the maximum force acting on the buffer, right? So that I can design appropriate design the reinforcement. I can also looking at if I have the tone or short buffer, what's going on, okay? I can even actually go further with a very complex system like what I have here, multiple buffer system using the computational model, or even go with a more complex problem here. I can use the net spring, it's a flexible spring. I can develop a computational model. This is a brief flow. I can model all of this process. I can predict when this sort of the flexible ring is going to break under the brief flow. Or move to the real case scenario where I can take the entire information in the real world to the computer and analyze one of these problems. This is an example of the modeling process that we develop in our laboratory using our own software. We develop our own software to release this. This is the system we predict without any automation. And now if you're having something here, you install some sort of automation here. You can actually predict this sort of thing. So this is a couple of examples that I can show how computational model can help to design or to reduce the disaster. Okay? So, sorry for running out of time. And with this, I would like to end my presentation. Any question? Please feel free to ask me. We spent a lot of time in the first part to interact about it. All right. Any question? All good? No question? Not interested in computational mechanics?
Maybe give a prize.
Yeah, that's right. I already give the prize. Now we still have 2 more prize. What question? Who wants to ask the question? We have 2 more prize. Come on, feel free to ask any question. Wow. That is the big prize, yeah?
That's the big prize.
That's the big prize.
Special pen.
It's very special pen. Yeah, feel free. Yep.
I want to question
Get a
again.
prize.
And I'm watching how watching for you. I am excited about mechanical method, but how we can apply this and to tackle this problem in reality. Do you have any project to apply this study?
This is one of the things that we are actually solving the real problem. You see, all of this is the actual DEM, the data we're taking from the Google Earth, and then we incorporate the information into the computer.
In Vietnam, in the Mekong Delta, it has a lot of
Yes.
a lot of river and love stability is extremely problem because when the soil unsaturated or saturated soil is easily to fail, collapse, and I think this is the best method to apply for the Mekong
That's
Delta.
right. Yeah. So at the moment, I'm working with the civil engineering department to develop sort of what they call early warning system. So we combine the technology, we combine the sensor that we taking the signal from the field to the computer, and then we analyze all of that process, and then we predict when the failure is going to occur, and then we issue the warning to the public. That's what we are currently working with the government.
Yeah, because when I participate in the workshop with the government in Đồng Tháp Forum,
Yeah.
it's until now about the device can predict about the slab stability now.
That's correct. Yeah, divine is the times, right?
Yes.
Because, if you're using a divine, you actually predict when the slope is going to collapse. So you're probably having very short time frames, only 30 minutes, in order to warning the warning, right? We issue the warning. But with this one, we can change the weather condition, and then we can predict where in advance. That's the proposal we proposed last year. With that most innovative. All right, we thank you for that. All right, this is very special. This is very special gift. You know, very special gift. Yeah. Yes. My gift, not special.
So this you have working with the beam.
Beam, yes, yes.
These can apply to this.
Definitely, yeah. That's what we are planning. So this sort of taking the Terran data in the field to the computer is the beam process.
Which is in process and phase work and is construction already done by few minutes. We just have in the climate.
This technology that we develop here is latest technology. It's a very new technology we developed recently.
So in the future,
In the future, we will consider that. Definitely, in the future, we need to incorporate with beam, in order to have a better sort of a tool to optimize the designs. Good question. One more. Yeah. Okay.
Now, I want to ask about the solutions that you guys are researching. So, for example, in Vietnam and other developing countries, we do not have access to resource of material in order to build solutions just like that. So, when you are designing a solution, what factors or what priorities do you take into account when constructing?
That's right. So that's also a good question. So they're talking about the material behavior and also the material properties. So when you develop a computing model, you need to predict the material behavior, and you need to, for example, if you want to simulate this field condition, you need to know the geological profile. What is the soil property in the field? What is the shear strength of the soil? So we need to conduct the field test in order to obtain the soil property. And then at the same time, we need to come up with a strategy to take into account the variability of the soil property in the field. It's a very complicated process, but all of these properties can be taken from the field test, okay? And then incorporate in the computing model. All right. I'm running out of the of the price, and thanks everyone for attending the lecture and also for questions regarding the program and then this basic knowledge. If you have any question, feel free to contact me with the research, and then if you have questions related to the program, please feel free to contact Ms. Jensen if you have any questions related to the program. Okay?
Yes.
All right. Thank you.
Thank you, Teacher Sean.
We have a little overview